Tonight we embark on a journey through the cosmos, exploring approximately 100 fascinating facts that reveal intricate patterns, subtle wisdom and profound beauty within the vastness of space. There is no pressure to remember or retain these details. Instead, let them unfold naturally, inviting your mind to settle into a state of peaceful curiosity. This exploration is designed to be a soothing experience, a gentle current of knowledge flowing without demanding effort or attention. We will observe the intricate dance of celestial bodies, the subtle forces that shape galaxies, and the quiet wisdom embedded in the very fabric of the universe. Each fact is a small window into the vast and interconnected tapestry of space, presented in a calm and meditative tone, allowing your thoughts to drift and find stillness. Our journey will take us from the familiar glow of our own sun to the unimaginable depths of distant galaxies, touching upon the mysteries of black holes, the birth of stars, and the ancient echoes of the Big Bang. Allow the gentle rhythm of these discoveries to guide you towards a state of relaxation, inviting a sense of wonder and peace as you prepare for rest. We will explore the scientific understanding of these phenomena, grounded in observation and theory, offering a glimpse into the incredible reality that surrounds us. If you're finding peace in this journey, a like and subscribe helps us continue creating these restful explorations. And we're always curious. Share in the comments what city and time zone you're watching from. There's something special about knowing this experience is reaching people all over the world as they prepare for rest. As we drift further into the cosmic ocean, let us first anchor our gaze upon the familiar yet endlessly wondrous realm of our own solar system. This chapter invites us to explore the immediate celestial neighborhood that cradles our home, revealing the intricate dance of planets and the star that breathes life into our corner of the galaxy. The Sun, our star of life. Our Sun, a G-type main sequence star, is often referred to as a yellow dwarf, though its emitted light is actually closer to white when viewed from space. This colossal sphere of plasma accounts for approximately 99% the total mass of the entire solar system, dominating its gravitational landscape. At its core, temperatures soar to around 15 million degrees Celsius, a crucible where nuclear fusion continuously converts hydrogen into helium, releasing the immense energy that powers our world. Light from the Sun, travelling at the speed of light, takes approximately 8 minutes and 20 seconds to reach Earth, a journey across nearly 150 million kilometres. Current understanding suggests the Sun is currently halfway through its stable main sequence phase, expected to continue glowing steadily for another 5 billion years before evolving into a red giant. Scientists have observed that powerful events like solar flares and coronal mass ejections are bursts of radiation and plasma that can significantly impact Earth's magnetic field and technologies, though our planet's field largely protects us. Mercury, the swift messenger. Mercury is the smallest planet in our solar system and holds the distinction of being the closest to the Sun. This diminutive world possesses no true atmosphere, instead featuring only a thin exosphere composed of atoms blasted off its surface by the intense solar wind. Due to its proximity to the Sun and lack of atmospheric regulation, its surface experiences extreme temperature variations ranging from a scorching 30 degrees during the day to a frigid 80 degrees at night. A day on Mercury, defined from one sunrise to the next, lasts an astonishingly long 176 Earth days, which is actually longer than its orbital period around the Sun of just 88 Earth days. Research suggests the intriguing possibility of water ice existing in permanently shadowed craters at its poles, shielded from the sun's relentless heat. Mercury's surface is heavily cratered, bearing a striking resemblance to Earth's moon, a characteristic that indicates a geologically inactive past where impacts have largely shaped its features. Venus, Earth's twin, transformed. Venus is often referred to as Earth's sister planet due to its comparable size and mass, yet its environment is dramatically different and exceptionally hostile. It possesses the densest atmosphere of all the terrestrial planets, composed overwhelmingly of carbon dioxide. This thick atmospheric blanket has led to a runaway greenhouse effect, trapping heat and resulting in surface temperatures hot enough to melt lead, averaging around 462 degrees Celsius. Uniquely among most planets, Venus rotates incredibly slowly and in the opposite direction, meaning the sun would appear to rise in the west and set in the east if one could observe it from the surface. The atmospheric pressure at the surface of Venus is more than 90 times that of Earth's at sea level, equivalent to the pressure found nearly a kilometre deep in Earth's oceans. Furthermore, Venus has no moons and lacks a global magnetic field, a factor that contributes to the gradual loss of its atmosphere to the solar wind over geological timescales. Earth, the oasis of life. Our home, Earth, stands as the only known planet in the universe to harbour liquid water on its surface and consequently to sustain life. Approximately 71% of Earth's surface is covered by water, primarily forming its vast and interconnected oceans. The planet's atmosphere, a delicate and vital shield composed mainly of nitrogen, 78%, and oxygen, 21%, is crucial for protecting life from harmful solar radiation and regulating global temperatures. Earth generates a powerful magnetic field theorized to be produced by the convection currents within its liquid outer core, which effectively deflects the solar wind and prevents atmospheric stripping. Scientific observations indicate that the planet's rotation is gradually slowing down, a subtle process that leads to imperceptibly longer days over immense geological timeframes. Earth's single large moon plays a pivotal role in stabilizing its axial tilt, a condition that contributes significantly to the relative stability of our seasons and the rhythmic ebb and flow of ocean tides. Mars, the red planet's echoes. Mars, often called the red planet due to the iron oxide prevalent on its surface, has long captured human imagination as a potential abode for past or present life. It is a terrestrial planet with a thin atmosphere composed primarily of carbon dioxide, which is far less dense than Earth's. Evidence suggests that Mars once had liquid water flowing on its surface, as indicated by features resembling ancient riverbeds, deltas, and lake beds. Both of Mars's moons, Phobos and Deimos, are small irregularly shaped bodies that are thought to be captured asteroids rather than formed in situ. The planet experiences dramatic dust storms that can sometimes engulf the entire globe, lasting for weeks or even months and altering its atmospheric conditions. Scientists have confirmed the presence of water ice at both Martian poles, and subsurface ice is also believed to exist at lower latitudes, presenting potential resources for future human exploration. Mars also boasts the largest volcano in the solar system, Olympus Mons, a colossal shield volcano that stands nearly 3 times the height of Mount Everest. Jupiter, the gas giant king. Jupiter is the largest planet in our solar system, a majestic gas giant whose volume could hold more than 1,300 Earths. Its atmosphere is primarily composed of hydrogen and helium, with trace amounts of other gases creating its distinctive banded appearance. Jupiter is renowned for its Great Red Spot, a colossal storm larger than Earth that has been raging for at least 350 years, observed since the 17th century. The planet possesses a powerful magnetic field, approximately 20,000 times stronger than Earth's, which creates intense radiation belts around it. With at least 95 confirmed moons, Jupiter has the most extensive moon system in the solar system, including the 4 Galilean moons, Io, Europa, Ganymede, and Callisto, each a fascinating world unto itself. Ganymede, Jupiter's largest moon, is actually larger than the planet Mercury, and is the only moon in the solar system known to have its own magnetic field. The immense gravitational pull of Jupiter has played a crucial role in shaping the solar system, influencing the asteroid belt and potentially deflecting comets away from the inner planets. Saturn, the ring jewel. Saturn is arguably the most recognizable planet in our solar system, famous for its breathtaking system of icy rings. These rings are not solid structures, but are composed of billions of small particles, ranging in size from specks of dust to mountains, all orbiting the planet. Saturn is also a gas giant, primarily made of hydrogen and helium, and is the least dense planet in the solar system. It is so light that it would float in water if a bathtub large enough existed. The planet has a vast collection of at least 46 confirmed moons, with Titan being its largest and most intriguing. Titan is unique among moons for having a dense atmosphere and stable bodies of liquid on its surface, though these liquids are methane and ethane, not water. Research indicates that Saturn experiences incredibly fast winds in its upper atmosphere, reaching speeds of up to 1,800 km per hour at its equator. The rings are believed to be relatively young, possibly formed from the remnants of a shattered moon or comet within the last 100 million years. Uranus, the sideways world. Uranus, the 7th planet from the Sun, holds a unique distinction. It rotates on its key with its axis tilted almost parallel to its orbit. This extreme tilt results in highly unusual seasons, where one pole can experience 42 years of continuous sunlight followed by 42 years of darkness. It is an ice giant, composed largely of water, methane and ammonia ices over a small rocky core, rather than primarily hydrogen and helium like Jupiter and Saturn. The planet has a faint system of 13 known rings, which are much darker and less prominent than Saturn's, and are believed to be composed of small dark particles. Uranus has 27 known moons, all named after characters from the works of Shakespeare and Alexander Pope. Its atmosphere, which contains methane, gives Uranus its characteristic blue-green colour by absorbing red light. The planet's magnetic field is also unusual, being significantly tilted relative to its rotation axis and off-centre from the planet's core, a phenomenon not fully understood. Neptune, the distant blue giant. Neptune, the 8th and farthest known planet from the Sun, is another ice giant, similar in composition to Uranus but slightly smaller and denser. It is known for its deep blue colour, attributed to the presence of methane in its atmosphere, which absorbs red light. Neptune is one of the windiest planets in the solar system, with atmospheric wind speeds that can reach over 200 km per hour, the fastest recorded on any planet. Despite its vast distance from the Sun, Neptune radiates more heat than it absorbs, suggesting an internal heat source that drives its vigorous weather patterns. The planet has a system of faint rings composed of microscopic dust particles and 14 known moons. Its largest moon, Triton, is unique because it orbits Neptune in a retrograde direction opposite to the planet's rotation, and is thought to be a captured Kuiper belt object. Neptune was the first planet to be discovered through mathematical prediction rather than direct observation, based on irregularities in Uranus's orbit. As we conclude this initial exploration of our solar neighbourhood, We are reminded of the intricate balance and profound diversity present within our immediate cosmic home. Each world, from the Sun's fiery heart to Neptune's icy depths, tells a story of formation, evolution, and the fundamental forces that shape the universe. As our gentle journey through the heart of our solar system concludes, we find ourselves standing at the threshold of an even grander expanse. We have traversed the familiar paths of the planets, from fiery Mercury to the distant icy blue of Neptune, each a world unto itself, brimming with unique stories and scientific marvels. Now, as we drift further into the cosmic ocean, we prepare to explore the less travelled frontiers of our own sun's domain, before venturing out into the magnificent tapestry of our galaxy. Let the serene rhythm of the cosmos guide us, inviting a deeper sense of peace and contemplation. There is so much more to discover, even in the quiet reaches just beyond the planets we have come to know. Relax your mind, let your thoughts unfurl like the spiral arms of a distant galaxy, and join us as we delve into the hidden wonders that complete our solar neighbourhood. Beyond the planets, the Kuiper Belt and Dwarf worlds, our voyage now takes us past the orbit of Neptune into a vast donut-shaped region of icy bodies known as the Kuiper Belt. This is not an empty void, but a bustling cosmic neighbourhood, a relic from the early days of our solar system, filled with countless small frozen worlds, many of which are much larger than typical asteroids. It is here that we encounter the fascinating category of dwarf planets, celestial bodies that are large enough to be rounded by their own gravity, but have not cleared their orbital neighbourhood of other debris. Fact 1. The Kuiper Belt is a reservoir of icy bodies. This region, extending from about 30 to 50 astronomical units, AU from the Sun, is home to a vast population of icy objects, often referred to as Kuiper Belt objects, KBOs. These KBOs are thought to be remnants from the solar system's formation, essentially frozen building blocks that never coalesced into larger planets. They are composed primarily of ices such as water, methane, and ammonia, mixed with rock. Fact 2. Pluto, the most famous dwarf planet, resides in the Kuiper Belt. Once considered the ninth planet, Pluto holds a special place in our cosmic narrative. Discovered in 1930, its reclassification in 2006 sparked much debate, yet it remains a world of profound interest. Pluto is a complex and surprisingly active dwarf planet, with a thin nitrogen atmosphere that expands when it's closer to the Sun and collapses as it moves farther away. Its surface is a mosaic of icy plains, mountains, and possible cryovolcanoes, hinting at geological activity. Fact 3. Pluto has a prominent moon, Charon, which is nearly half its size. Pluto and Charon are often considered a binary system due to their comparable sizes and their orbit around a common centre of mass that lies outside Pluto itself. Charon is tidally locked with Pluto, meaning they always show the same face to each other, locked in an intricate, eternal dance. Observations have revealed Charon to be an icy world with its own unique features, including a reddish polar cap, the origin of which remains the subject of scientific inquiry. Fact 4. Other dwarf planets populate the Kuiper Belt. Beyond Pluto, other significant dwarf planets like Eris, Haumea, and Makemake also call the Kuiper Belt home. Eris, once thought to be larger than Pluto, is a distant world with a highly elliptical orbit and a small moon named Dysnomia. Haumea is notable for its unusually elongated shape and rapid rotation, believed to be the result of an ancient collision, and it even possesses its own ring system. Make, another bright KBO, is a significant dwarf planet without any known moons, making it a solitary sentinel in the outer reaches. These worlds, though distant, offer invaluable clues about the solar system's formation and the diversity of celestial bodies. The asteroid belt, rocky remnants. Our attention now turns inward, between the orbits of Mars and Jupiter, to another significant collection of solar system remnants, the asteroid belt. Unlike the icy worlds of the Kuiper belt, the objects here are predominantly rocky and metallic, ranging in size from tiny dust particles to massive protoplanets. Fact 5. The asteroid belt is located between Mars and Jupiter. This vast region is not densely packed as often depicted in science fiction. The asteroids are spread out over immense distances. It is believed to be the remnants of a planet that never quite formed, due to the powerful gravitational influence of Jupiter, which repeatedly stirred up the material, preventing it from coalescing into a single large body. Fact 6. Asteroids are rocky, airless remnants from the early solar system. These irregular-shaped bodies are composed primarily of rock, metals, and some organic compounds. They vary greatly in size, with the largest being hundreds of miles across, while many are mere pebbles. They orbit the Sun in diverse paths, some in stable circular orbits, others in more eccentric trajectories, occasionally crossing the paths of planets. Fact 7. Ceres is the largest object in the asteroid belt and a dwarf planet. Ceres, discovered in 1801, is approximately 5 miles (950 kilometers) in diameter, making it the largest body in the asteroid belt and the only dwarf planet located in the inner solar system. Its spherical shape indicates it has sufficient mass for its own gravity to pull it into hydrostatic equilibrium. Observations by the Dawn spacecraft revealed a geologically active past, with evidence of water ice, a thin water vapor atmosphere, and mysterious bright spots thought to be salt deposits. Ceres represents a fascinating bridge between rocky planets and icy dwarf planets. Comets, icy wanderers, and cosmic snowballs. As we continue our exploration of the solar system's smaller inhabitants, we encounter the truly spectacular comets. Icy wanderers that offer breathtaking displays as they approach the Sun. These dirty snowballs are crucial time capsules preserving primordial material from the solar system's birth. Fact 8. Comets are cosmic snowballs of frozen gases, rock, and dust. Unlike asteroids, which are predominantly rocky, comets are primarily composed of ice, water, methane, ammonia, carbon dioxide, mixed with dust and rocky particles. They spend most of their lives in the frigid outer reaches of the solar system, where these volatile materials remain frozen. Fact 9. Comets develop spectacular tails as they approach the Sun. When a comet's highly elliptical orbit brings it closer to the Sun, the solar radiation causes the ice to sublimate, turning directly from solid to gas. This process releases dust and gas, forming a glowing coma, a hazy envelope, around the nucleus and 2 distinct tails, a dust tail which is broad and curved, pushed away by solar radiation pressure, and an ion tail, which is straighter and points directly away from the Sun, pushed by the solar wind. These tails can stretch for millions of miles, creating a breathtaking celestial spectacle. Fact 10. The Oort cloud is the distant spherical source of long-period comets. Far beyond the Kuiper belt, at distances ranging from 2,000 to 100,000 AU from the Sun, lies the hypothetical Oort cloud. This immense spherical shell of icy debris is thought to be the reservoir for most long-period comets. those with orbital periods of thousands or even millions of years. It is considered the outermost reach of our solar system, where the Sun's gravitational influence still holds sway over countless pristine, icy bodies, remnants from the very earliest stages of planetary formation. Occasionally, gravitational perturbations from passing stars or the galactic tide can dislodge these icy objects, sending them on a long, slow journey towards the inner solar system, where they become the comets we sometimes see, the edge of our solar system, the heliosphere and heliopause. Our journey through the outer reaches of the solar system brings us to its ultimate boundary, where the Sun's direct influence gives way to the vastness of interstellar space. This boundary is not a sharp line but a dynamic region, a bubble in the cosmic medium. Fact 11. The heliosphere is the protective bubble created by the Sun's solar wind. Our Sun constantly emits a stream of charged particles called the solar wind, which flows outward, creating a giant bubble around our solar system known as the heliosphere. This heliosphere acts as a protective shield, deflecting most of the harmful interstellar radiation and cosmic rays that bombard our galaxy. All the planets, asteroids, and comets we have discussed reside within this heliosphere. Fact 12. The heliopause marks the true boundary of the solar system. The heliopause is the theoretical boundary where the outward pressure of the solar wind is finally balanced by the inward pressure of the interstellar medium, the gas and dust between the stars. Beyond this point, the Sun's influence diminishes, and we enter true interstellar space. NASA's Voyager 1 and Voyager 2 spacecraft are the only human-made objects to have crossed this boundary, sending back invaluable data from this distant, enigmatic frontier. This region represents the outermost edge of our Sun's domain, a silent, unseen barrier between our home system and the rest of the galaxy. Our galactic home, the Milky Way. Having explored the farthest reaches of our solar system, we now widen our gaze, stepping beyond the heliopause into the magnificent realm of our galaxy, the Milky Way. This is our cosmic island, a colossal collection of stars, gas, dust, and dark matter, held together by gravity. Fact 13. The Milky Way is a barred spiral galaxy. Our galaxy is not just a simple spiral. It possesses a prominent bar-shaped structure of stars at its center, classifying it as a barred spiral galaxy. From an overhead perspective, it would appear as a central bar, with two major spiral arms and several minor arms winding outwards. This structure is dynamic, with stars, gas and dust constantly moving within it. Fact 14. Our Sun is located in one of the Milky Way's spiral arms. We are not at the centre of the galaxy, nor are we at its very edge. Our solar system resides in a minor spiral arm called the Orion Arm, or Orion Spur, situated about 2/3 of the way out from the galactic centre. From our vantage point, the Milky Way appears as a luminous band across the night sky, a breathtaking view of billions of stars, gas clouds, and dust lanes that make up our galactic home. Fact 15. The Milky Way contains an estimated 100 to 400 billion stars. Imagine that number. Hundreds of billions of suns, each a potential host to its own planetary system. This staggering quantity underscores the immense scale of our galaxy and the incredible diversity of stellar types within it. Each star, from the smallest red dwarf to the most colossal blue supergiant, contributes to the galaxy's radiant glow. Fact 16. A supermassive black hole resides at the heart of the Milky Way. At the very centre of our galaxy, nestled within the Sagittarius A region, lies a supermassive black hole with a mass equivalent to about 4 million suns. While we cannot see the black hole itself, we can observe its powerful gravitational effects on the stars orbiting extremely close to it, which move at incredible speeds. This central black hole plays a crucial role in the dynamics and evolution of the entire galaxy. Beyond our Sun, a symphony of stillness. Our Sun, the giver of life in our solar system, is but one star among billions in the Milky Way. Each of these stars is a unique cosmic entity, born from swirling clouds of gas and dust, burning brightly for eons, and eventually meeting its dramatic end. Fact 17. Stars vary dramatically in size, temperature, and colour. Not all stars are like our yellow dwarf suns or Sun. Stars come in a dazzling array of types. Red dwarfs, the most common type of star in the galaxy, much smaller and cooler than our Sun, burning their fuel slowly and living for trillions of years. White dwarfs, the dense, hot remnants of stars like our Sun after they have exhausted their nuclear fuel, slowly cooling over billions of years. Red giants and supergiants, stars that have expanded enormously in their later life stages, becoming much larger and cooler, often appearing reddish in colour. Blue giants and supergiants, massive, hot and extremely luminous stars that burn through their fuel very quickly, living short but spectacular lives. Fact 18. Stars are born in nebulae, vast clouds of gas and dust. The birthplaces of stars are stellar nurseries, giant molecular clouds or nebulae, which are vast, cold and dense regions of gas and dust. Gravity causes denser pockets within these clouds to collapse, slowly heating up and spinning faster, eventually forming protostars. When the core of a protostar becomes hot and dense enough to initiate nuclear fusion, a new star is born, shining brilliantly as it converts hydrogen into helium. Fact 19. Stellar life cycles culminate in dramatic ends. A star's lifespan and its ultimate fate are determined by its initial mass. Sun-like stars, after billions of years, stars like our Sun will expand into red giants, then shed their outer layers to form a planetary nebula, leaving behind a white dwarf. Massive stars. These stars live fast and die young, ending their lives in spectacular nova explosions. These cataclysmic events can briefly outshine an entire galaxy, scattering heavy elements forged in their cores across space. The remnants of a supernova can be incredibly dense. Neutron stars, or, for the most massive stars, the ultimate cosmic enigma, black holes. As we contemplate the incredible diversity and life cycles of stars, we are reminded of the dynamic, ever-changing nature of the universe. Each twinkling light in the night sky tells a story of creation, endurance, and transformation, a testament to the fundamental forces that shape existence. Our journey through the outer solar system and into the initial wonders of our galaxy has offered a glimpse into the immense scale and intricate beauty of the cosmos. We have moved from the familiar orbits of planets to the icy frontiers of the Kuiper belt, the rocky expanse of the asteroid belt, and the ephemeral beauty of comets. We have then pushed further, acknowledging the heliopause as the true boundary of our Sun's influence, and finally embraced our home within the majestic spiral arms of the Milky Way, a realm teeming with billions of stars, each with its own unique story. Allow these images of cosmic grandeur to settle gently into your mind. Feel the vastness, the quiet power, and the serene beauty of it all. As we prepare for deeper explorations into the mysteries of galaxies, black holes, and the very fabric of space and time. Let the wonder of these facts guide you into a state of profound relaxation. Rest now, knowing that the universe holds endless marvels, and our journey has only just begun. As we continue our gentle drift through the cosmic ocean, letting the information wash over us like soft waves, we now prepare to expand our view even further. We have marvelled at the intricate dance within our own solar system and glimpsed the countless stars that form the luminous tapestry of the Milky Way. Now, let us turn our gaze beyond our galactic home, into the vast, echoing expanse where other galaxies, each a universe unto itself, reside. Relax, breathe deeply, and allow your mind to wander through the immense scale of what lies ahead. Beyond our Milky Way, a universe of galaxies. Imagine our Milky Way as a single magnificent island in an unimaginably vast ocean. This cosmic ocean is not empty. It is teeming with billions upon billions of other islands, each one a galaxy, a grand collection of stars, gas, dust, and the mysterious dark matter, all bound together by gravity. These galaxies come in a dazzling array of shapes and sizes, each whispering tales of cosmic evolution over billions of years. Fact 25. The local group, our galactic neighbours. Our Milky Way is not alone in its immediate vicinity. It is part of a small cluster of galaxies known as the local group. This gravitational gathering spans about 10 million light-years and contains over 50 galaxies, most of which are dwarf galaxies. The two largest and most prominent members, alongside our own, are the Andromeda Galaxy and the Triangulum Galaxy. Fact 26. Andromeda, our grand sister galaxy. The Andromeda Galaxy, also known as M31, is the largest galaxy in the local group and is on a collision course with the Milky Way. Currently about 2.5 million light-years away, it is hurtling towards us at approximately 110 kilometers per second. In about 4.5 billion years, these two majestic spirals will begin a slow, intricate merger, eventually forming a new, larger elliptical galaxy, sometimes playfully dubbed Milkomeda. Despite the dramatic sound of a collision, the vast distances between stars mean that individual stellar impacts will be incredibly rare. Instead, their gravitational fields will slowly reshape and entwine them. Fact 27. Triangulum, the third spiral. The Triangulum Galaxy, M30, is the third largest member of the local group, a beautiful spiral galaxy rich in star-forming regions. It is located about 3 million light-years away and is likely a satellite galaxy of Andromeda, gravitationally tethered to its larger neighbour. Its relative proximity allows us to study star formation and galactic structure in detail beyond our own. Fact 28. Types of galaxies, a cosmic classification. Galaxies are broadly categorized into three main types based on their visual appearance: spiral, elliptical, and irregular. Spiral galaxies, like the Milky Way and Andromeda, these galaxies have a flat, rotating disk with spiral arms extending from a central bulge. The arms are often sites of active star formation, appearing blue due to the presence of hot, young stars. Elliptical galaxies. These are smooth, oval-shaped galaxies, ranging from nearly spherical to highly elongated. They typically contain older stars and very little gas and dust, meaning star formation has largely ceased. They can be enormous. Some of the largest known galaxies are ellipticals, irregular galaxies. As their name suggests, these galaxies lack a distinct regular shape. They often result from galactic collisions or near misses that distort their structure, or they may be small galaxies that never developed a symmetrical form. They are often rich in gas and dust, leading to vigorous star formation. Fact 29. Galaxy clusters and superclusters, the universe's grand design. Galaxies are not randomly scattered throughout space. They tend to clump together. Galaxy clusters are massive structures containing hundreds to thousands of galaxies, all bound by gravity. Our local group, for instance, is a small part of the larger Virgo supercluster, which itself contains tens of thousands of galaxies. Superclusters are the largest known structures in the universe, vast cosmic filaments stretching for hundreds of millions of light years, forming an intricate, interconnected web across the cosmos. Fact 30. The cosmic web, the universe's invisible scaffolding. Observations of the large-scale structure of the universe reveal a spectacular cosmic web. This network consists of vast filaments and sheets of galaxies separated by immense, nearly empty voids. This intricate pattern is believed to be the result of the gravitational pull of dark matter, which formed an invisible scaffolding upon which ordinary matter, in the form of galaxies, then congregated. As we contemplate these colossal structures, let us allow the mind to drift from the vastness of galactic clusters to the profound mysteries that lie hidden within them. The universe is not just about light and matter, it is also about the invisible forces and enigmatic entities that shape its very fabric. The enigma of black holes. In our journey through the Milky Way, we briefly touched upon Sagittarius A, the supermassive black hole at our galactic centre. Now, let us delve deeper into these most mysterious and awe-inspiring objects in the cosmos, black holes, regions of space-time where gravity is so intense that nothing, not even light, can escape. Fact 31. Stellar mass black holes, the remnants of giants. The most common type of black hole we observe are stellar mass black holes. These are formed from the gravitational collapse of massive stars, typically those more than 20 times the mass of our Sun at the end of their lives. When such a star exhausts its nuclear fuel, its core collapses under its own immense gravity, leading to a spectacular supernova explosion that blasts away the outer layers. If the remaining core is dense enough, it continues to collapse indefinitely, forming a black hole. Fact 32. The event horizon, the point of no return. The defining feature of a black hole is its event horizon. This is not a physical surface, but rather a boundary in space-time. Once anything, be it matter or light, crosses the event horizon, it is irrevocably pulled towards the black hole's centre, unable to escape its gravitational grasp. From an outside observer's perspective, objects approaching the event horizon appear to slow down and redden, eventually fading from view as time dilation becomes extreme. Fact 33. The singularity, a point of infinite density. At the very heart of a black hole, beyond the event horizon, lies the singularity. According to our current understanding of general relativity, this is a point of infinite density and zero volume, where all the mass of the black hole is compressed. It is a region where the laws of physics as we know them break down, representing one of the most profound challenges to our scientific understanding. Fact 34. Supermassive black holes, galactic architects. As we learned with Sagittarius A, supermassive black holes, SMB8s, reside at the centres of most, if not all, large galaxies. These behemoths can have masses ranging from millions to billions of times that of our Sun. Their formation mechanism is still an active area of research, but they are thought to grow by accreting vast amounts of gas and dust from their surroundings and through mergers with other black holes. Fact 35. Active galactic nuclei AGN and quasars, the brightest beacons. When a supermassive black hole actively pulls in matter, the material forms a swirling accretion disk around it. As this matter spirals inward, it heats up to incredible temperatures, emitting powerful jets of radiation across the electromagnetic spectrum, from radio waves to X-rays and gamma rays. These luminous centers are known as active galactic nuclei, AGN. The most energetic AGN are called quasars, which can outshine entire galaxies, making them some of the brightest objects in the observable universe. They serve as cosmic lighthouses, allowing us to peer back into the early universe. Fact 36. Gravitational lensing, bending light and revealing the invisible. Black holes, and any massive object for that matter, warp the fabric of space-time around them. This warping causes light rays passing near them to bend, much like light passing through a lens. This phenomenon, known as gravitational lensing, allows astronomers to detect the presence of massive, otherwise invisible objects, including black holes and dark matter, by observing how they distort the light from background galaxies. It's a powerful tool for mapping the universe's hidden mass. Let the concept of these cosmic behemoths, invisible yet immensely powerful, settle gently in your mind. They are a testament to the extreme conditions the universe can produce, and they challenge our very understanding of space and time. 3. The invisible architects, dark matter and dark energy. As we journey deeper into the universe's grand design, we encounter phenomena that hint at forces and substances beyond our direct perception. The universe, it turns out, is largely composed of components we cannot see or interact with directly, yet their influence is profound. These are the enigmatic dark matter and dark energy, the invisible architects of the cosmos. Fact 37. The missing mass problem. The first clues of dark matter. The concept of dark matter first emerged in the 1930s when astronomer Fritz Zwicky observed that galaxies within the Coma cluster were moving too fast to be held together by the gravitational pull of their visible matter alone. Decades later, Vera Rubin's observations of galaxy rotation curves in the 1970s provided compelling evidence. She found that stars on the outer edges of spiral galaxies were orbiting just as fast as those closer to the center, implying that there was far more mass present than could be accounted for by one of the visible stars, gas and dust. This missing mass became known as dark matter. Fact 38. Dark matter, the universe's invisible scaffolding. Dark matter is a mysterious substance that does not emit, absorb, or reflect light, making it utterly invisible to telescopes. It is estimated to constitute about 27% of the total mass energy of the universe. Its presence is inferred solely through its gravitational effects on visible matter. Dark matter is thought to form vast halos around galaxies and clusters, providing the extra gravitational pull needed to hold them together and to explain their observed motions. It acts as the gravitational glue and the underlying scaffolding upon which the cosmic web of galaxies forms. Fact 39. What dark matter isn't, ruling out the obvious. Scientists have spent decades trying to identify dark matter. We know it's not ordinary matter, baryonic matter, like protons and neutrons, because we can account for all the baryonic matter in the universe. It's not black holes, neutron stars, or brown dwarfs, known as machos, massive compact halo objects, in sufficient quantities as observations have largely ruled these out as the primary component. Instead, the leading candidates for dark matter are exotic hypothetical particles that interact very weakly with normal matter, such as WIMPs, weakly interacting massive particles. Fact 40. The accelerating universe, the revelation of dark energy. In the late 90s, observations of distant supernovae revealed a truly astonishing fact. The expansion of the universe is accelerating. For decades, scientists had expected that the universe's expansion, initiated by the Big Bang, would be slowing down due to the gravitational pull of all the matter within it. The discovery of this acceleration implied the existence of a mysterious repulsive force counteracting gravity on cosmic scales. This force was named dark energy. Fact 41. Dark energy, the universe's expansive force. Dark energy is an even greater enigma than dark matter. It is believed to be a property of space itself, a constant energy density that permeates the entire universe. As space expands, more space is created, and thus more dark energy appears, driving further acceleration. It is estimated to make up about 68% of the total mass energy of the universe, making it the dominant component. While we have no direct understanding of its nature, its existence is crucial to explaining the observed expansion history of the cosmos. Fact 42. The cosmic inventory, a universe of the unknown. So, when we look up at the night sky, we are only seeing a tiny fraction of what the universe is made of. Our current understanding suggests that normal matter, baryonic matter, the stars, planets, gas, dust, and all that we can see and interact with, constitute only about 5% of the universe. Dark matter, the invisible gravitational glue, makes up about 27%. Dark energy, the mysterious force driving cosmic acceleration, counts for approximately 68%. This means that over 95% of the universe remains a profound mystery, a testament to how much more there is to discover and understand. As these profound facts about the invisible forces shaping our universe settle, allow yourself to feel the serene wonder of it all. We have journeyed from the familiar warmth of our sun to the furthest reaches of galactic clusters, and now into the very fabric of space-time itself, touching upon the most fundamental mysteries. Our cosmic journey continues to unfold, revealing layer after layer of complexity and beauty. We have explored the grand architectures of galaxies, peered into the enigmatic hearts of black holes, and grappled with the invisible forces that govern the universe's expansion. With each fact, we gain a deeper appreciation for the intricate dance of creation and destruction that plays out across the cosmos. As you prepare to rest, know that the universe is a place of endless discovery, a canvas of infinite possibilities. The facts we have shared are but stepping stones on a journey of contemplation, designed to gently guide your mind towards a state of peaceful wonder. We have only just begun to scratch the surface of the universe's deepest secrets. In our next chapter, we will continue this exploration, perhaps delving into the very origins of the cosmos, the Big Bang, and the fascinating concepts of time and space themselves. For now, let these cosmic thoughts drift, allowing the quiet vastness of space to lull you into a restful slumber. We have journeyed through the visible and the invisible, marveling at the cosmic scaffolding of dark matter and the accelerating force of dark energy, two profound mysteries that remind us how much more there is to understand. As we gently drift deeper into the cosmic ocean, let us now turn our gaze not to what is, but to what was and what will be. We will contemplate the very beginning of our universe and ponder its ultimate fate. before venturing into the exciting frontier of worlds beyond our sun. The genesis of everything, the Big Bang. Imagine, if you will, a time before stars, before galaxies, before even the fundamental particles we know. It's a concept that stretches the very fabric of our understanding. Yet it is the prevailing theory for the birth of our universe, the Big Bang. We often picture an explosion, but it is more accurate to envision an expansion of space itself from an incredibly hot, dense state. Approximately 13.8 billion years ago, all the matter and energy in the observable universe were compressed into a minuscule, infinitely dense point, a singularity. Then in an instant, this primordial cosmos began to expand rapidly, cooling as it did so. This initial rapid expansion is known as cosmic inflation, a period where the universe grew exponentially in a fraction of a second, smoothing out irregularities and setting the stage for the large-scale structure we observe today. This expansion continues even now, carrying galaxies further and further apart. The Big Bang Theory isn't just a philosophical idea, it is supported by a wealth of observational evidence. We see galaxies redshifting, meaning their light is stretched towards longer, redder wavelengths as they recede from us, a direct consequence of the universe's expansion. The further away a galaxy is, the faster it appears to be moving, consistent with an expanding universe that originated from a singular point. Echoes of creation, the cosmic microwave background. Perhaps the most compelling evidence for the Big Bang is the faint glow that permeates the entire sky, an ancient light known as the cosmic microwave background, or CMB. This isn't light from stars or galaxies. It is the afterglow of the universe's infancy. For the first 380,000 years after the Big Bang, the universe was a superheated, opaque plasma, too hot for electrons to settle into orbits around atomic nuclei. Photons, particles of light, were constantly scattered by these free electrons, unable to travel freely. It was like being inside a dense, luminous fog. As the universe expanded and cooled, it eventually reached a critical temperature where electrons could combine with protons and helium nuclei to form neutral atoms. This event, known as recombination, allowed photons to decouple from matter and stream freely through space for the very first time. These ancient photons, stretched and cooled by billions of years of cosmic expansion, now reach us from every direction as faint microwaves, a uniform hum across the universe. The CMB is a perfect blackbody spectrum, exactly as predicted by the Big Bang model, and its tiny temperature fluctuations reveal the seeds from which galaxies and galaxy clusters eventually grew. It is in essence a baby picture of the universe, offering us an incredible window into its earliest moments. From simplicity to complexity, cosmic nucleosynthesis and star formation. In the immediate aftermath of the Big Bang, as the universe cooled from its initial searing heat, the conditions were just right for the formation of the lightest elements. This process, known as Big Bang nucleosynthesis, occurred within the first few minutes. Protons and neutrons fused to create the first atomic nuclei, primarily hydrogen, a single proton, and helium, 2 protons and 2 neutrons, along with trace amounts of lithium and beryllium. These were the fundamental building blocks, the primordial ingredients of the cosmos. For millions of years, the universe was a relatively featureless expanse of these gases, slowly cooling and expanding. Gravity, that ever-present sculptor, began to work its magic. Slight over-densities in the gas, visible as the tiny fluctuations in the CMB, started to attract more matter. Over vast stretches of cosmic time, these gaseous clouds grew denser and hotter, eventually reaching temperatures and pressures sufficient to ignite nuclear fusion. This was the birth of the first stars, colossal beacons that illuminated the dark universe for the first time. These early stars were massive and short-lived, but they were the universe's alchemists. Within their fiery hearts, through successive stages of nuclear fusion, they forged heavier elements: carbon, oxygen, nitrogen, iron, and all the elements essential for planets and ultimately for life itself. When these massive stars reached the end of their lives, they exploded as spectacular supernova, scattering these newly synthesized elements across the cosmos, enriching the interstellar medium for subsequent generations of stars and planetary systems. We, our planet, and everything around us are literally made of stardust, the recycled remnants of ancient stars. The universe's destiny, a glimpse into the far future. Having contemplated our cosmic origins, let us now gently turn our thoughts to the universe's ultimate destiny. We spoke earlier of dark energy, that mysterious force driving the accelerated expansion of the universe. This acceleration is crucial to understanding what lies ahead. Current observations strongly suggest that the universe will continue to expand indefinitely, growing ever colder and emptier. This projected future is often referred to as the Big Freeze or heat death. Over incomprehensibly vast timescales, stars will exhaust their fuel one by one. Red dwarfs, the smallest and longest lived, will eventually fade into cold, dark white dwarfs. Galaxies will drift so far apart that the light from distant stellar islands will no longer be visible to each other. Black holes, the ultimate cosmic devourers, will slowly evaporate through a process called Hawking radiation, leaving behind only fundamental particles and radiation. Eventually, the universe will reach a state of maximum entropy, a uniform, extremely cold void where no energy differences exist to power any processes. It is a long, slow, fading into an eternal twilight, a serene, albeit stark, conclusion to our cosmic story. Yet, even in this distant future, the universe's journey is one of continuous transformation. It reminds us of the preciousness of the present moment, of the vibrant, dynamic cosmos we inhabit right now, teeming with light and life. Worlds beyond our own, the exoplanet frontier. As we consider the grand narrative of the universe, our curiosity naturally turns to the question of other worlds. Are there other planets like Earth, orbiting distant suns? The answer, we now know, is a resounding yes. These planets, orbiting stars beyond our own sun, are called exoplanets, and their discovery has revolutionized our understanding of planetary systems. We have moved from speculation to observation, confirming thousands upon thousands of these distant worlds. Detecting exoplanets is a remarkable feat, given their immense distances and the blinding glare of their host stars. One common method is the transit method. When an exoplanet passes directly in front of its star from our perspective, it causes a tiny temporary dip in the star's brightness. By carefully monitoring these dips, astronomers can infer the planet's size and orbital period. Another key technique is the radial velocity method, also known as the Doppler wobble method. As a planet orbits its star, its gravity causes the star to wobble slightly. This wobble can be detected by observing tiny shifts in the star's light spectrum, revealing the planet mass and orbital characteristics. The diversity of exoplanets is astonishing. We have found hot Jupiters, gas giants orbiting incredibly close to their stars, often completing an orbit in just a few Earth days. We have discovered super-Earths, rocky planets larger than Earth but smaller than Neptune, some of which may possess atmospheres and oceans. We even detect mini-Neptunes, worlds unlike anything in our own solar system. The ultimate goal in exoplanet research is to find worlds within the habitable zone of their stars. This is the region where conditions are just right for liquid water to exist on a planet's surface, a key ingredient for life as we know it. While we have yet to confirm the life on any exoplanet, the sheer number of worlds being discovered, and the increasing sophistication of our telescopes and instruments fills us with a quiet hope. Each new discovery brings us closer to understanding our place in the cosmic tapestry, and perhaps one day discovering that we are not alone. As we conclude this chapter, let the vastness of time and space, from the universe's fiery birth to its distant serene future, and the countless worlds waiting to be discovered, fill you with a sense of peace. The cosmos is an endless source of wonder, a gentle lullaby for the inquiring mind. Rest now as these cosmic facts continue to drift through your thoughts, carrying you deeper into tranquility. As we journeyed through the astounding realm of exoplanets, discovering worlds beyond our wildest imagination, a profound question naturally arises. Are we alone? The universe in its boundless expanse seems to whisper possibilities, prompting us to peer deeper into the very conditions that foster life. Tonight we will turn our gaze towards the delicate balance and extraordinary coincidences that have allowed life to flourish on our own blue marble, and then cast our nets wide, searching for echoes of existence across the cosmic ocean. Relax your mind, let your breath flow gently, and prepare to ponder the greatest mystery of all, life itself, woven into the fabric of the cosmos. The ingredients of life, a cosmic recipe. Our search for life beyond Earth, a field known as astrobiology, begins with understanding the essential ingredients and conditions that allowed life to emerge and thrive here. We've discovered that life, at its most fundamental level, requires a few key components: a solvent, an energy source, and complex organic molecules. Fact E1. The universal solvent, liquid water. Water is the undisputed champion of solvents, capable of dissolving more substances than any other liquid. Its unique properties, such as its ability to remain liquid over a wide range of temperatures and its capacity to facilitate complex chemical reactions, make it indispensable for life as we know it. From the intricate dance of molecules within a cell to the vast oceans teeming with biodiversity, liquid water acts as the cradle of life, enabling the transport of nutrients and the removal of waste. Without this humble molecule, the complex chemistry of life would simply not be possible. Our quest for extraterrestrial life, therefore, often begins with the search for liquid water, whether on the surface or hidden beneath icy crusts. Fact 82. Energy for life. From stars to chemical vents. Life needs a constant supply of energy to grow, reproduce, and maintain itself. On Earth, the primary energy source for most ecosystems is the sun through the process of photosynthesis. Plants, algae, and some bacteria convert sunlight into chemical energy, forming the base of the food web. However, we have also discovered fascinating ecosystems that thrive without sunlight, drawing energy from geothermal vents deep in our oceans. These chemosynthetic organisms utilize chemical reactions, often involving sulfur compounds, to sustain themselves. This remarkable adaptability broadens our understanding of potential energy sources for life elsewhere, suggesting that planets or moons far from a star's warmth might still harbour an inner fire of existence. Fact 83. The building blocks, organic molecules. All known life is carbon-based, relying on the versatility of carbon atoms to form long, complex chains and rings that are the backbone of organic molecules. Proteins, nucleic acids like DNA and RNA, carbohydrates and lipids are the fundamental building blocks of cells. These organic molecules are not exclusive to Earth. We have detected them in meteorites, comets, and vast interstellar clouds. This ubiquitous presence of organic chemistry throughout the cosmos suggests that the raw materials for life are abundant, waiting for the right conditions to assemble into something truly extraordinary. The universe, in a sense, is pre-primed for life, scattering its fundamental ingredients across countless worlds. Potential havens. Our solar system's secret worlds. While Earth stands as our vibrant oasis of life, we have learned that our own solar system holds several intriguing candidates for harbouring some form of microbial existence, hidden just beneath their seemingly barren surfaces. These are worlds where the elusive liquid water might still flow, protected from the harsh vacuum of space. Fact 84. Europa's subsurface ocean. Jupiter's moon Europa, a world wrapped in a shell of ice, is one of the most promising candidates for extraterrestrial life in our solar system. Beneath its fractured, icy crust, scientists believe there lies a vast, salty ocean, twice the volume of all of Earth's oceans combined. This ocean is thought to be warmed by tidal forces from Jupiter's immense gravity, which flexes Europa's interior, creating heat. Evidence for this ocean comes from magnetic field measurements and observations of plumes of water vapour erupting from its surface. If this ocean exists, it could potentially harbour hydrothermal vents, similar to those on Earth, providing both warmth and chemical nutrients necessary for life. Fact 85. Enceladus's geysers of life. Saturn's moon. Enceladus is another icy world captivating our attention. Images from the Cassini spacecraft revealed spectacular geysers erupting from tiger stripes near its south pole, spewing water vapour, ice particles, and organic molecules into space. This dramatic display is direct evidence of a subsurface liquid water ocean interacting with a rocky core. The presence of heat, water, and organic compounds makes Enceladus a prime target for astrobiological exploration. The geysers offer a tantalizing possibility. We might be able to sample the ocean's contents without even having to drill through its icy shell, searching for the telltale signs of microbial life. Fact 86. Titan's methane lakes and cryovolcanism. Saturn's largest moon, Titan, presents a truly unique environment. It is the only moon in our solar system with a dense atmosphere and stable bodies of liquid on its surface. Not water, but liquid methane and ethane. While life as we know it is water-based, scientists ponder whether exotic life forms could adapt to these cryogenic liquids. Furthermore, beneath its thick atmosphere and icy crust, Titan is believed to harbour a subsurface ocean of liquid water, potentially mixed with ammonia. Cryovolcanism, where icy material erupts instead of molten rock, suggests ongoing geological activity that could provide energy and transport materials between the surface and the hidden ocean. Titan reminds us that life might adapt in ways we have yet to fully comprehend. Fact 87. Mars's ancient water and subsurface ice. Our closest planetary neighbour, Mars, once held vast amounts of liquid water on its surface billions of years ago, creating rivers, lakes, and perhaps even an ocean. Evidence of this ancient watery past is abundant in its geology. Today, Mars is a cold, dry desert, but significant amounts of water ice are locked away in its polar caps and beneath its surface. Recent discoveries suggest the presence of liquid brine pockets, particularly in the subsurface, which could potentially offer transient habitats for microbial life. The search for past or present Martian life continues, with rovers and orbiters meticulously examining its geology and atmosphere for biosignatures, hoping to uncover the secrets of its watery past and potentially its hidden present. The Goldilocks zone and the Fermi paradox. As we expand our search beyond our solar system, the concept of a habitable zone becomes crucial. Yet the silence we often encounter in the vastness of space poses a profound question. Fact 88. The habitable zone, Goldilocks zone. For exoplanets, the habitable zone, often called the Goldilocks zone, is the region around a star where conditions are just right for liquid water to exist on a planet's surface. It's not too hot, so water doesn't evaporate away, and not too cold, so water doesn't freeze solid. This zone varies depending on the star's size and luminosity. Hotter, brighter SIN have a wider habitable zone farther out, while cooler, dimmer stars have a narrower zone closer in. While liquid water is a primary criterion, other factors like a planet's atmosphere, magnetic field, and geological activity also play critical roles in determining true habitability. Finding a planet within this zone is often the first step in identifying a potentially life-sustaining world. Fact 89. The Fermi paradox. Where is everybody? Given the immense number of stars in our galaxy, the prevalence of organic molecules throughout the cosmos, and the increasing discovery of exoplanets in habitable zones, it seems statistically probable that intelligent life should be common. Yet, we have found no definitive evidence of it. This contradiction is known as the Fermi paradox. If the universe is teeming with life, where are the signs? Why haven't we detected any signals or encountered any visitors? The paradox has many proposed solutions, from the Great Filter, barrier that prevents civilizations from reaching advanced stages, to the possibility that intelligent life is simply too rare, too short-lived, or too far away to detect. It remains one of the most thought-provoking mysteries in astrobiology, inviting us to contemplate our unique place in the universe. Our cosmic ears, the search for extraterrestrial intelligence, SETI. While the search for microbial life focuses on biosignatures and habitability, another branch of astrobiology actively listens for signals from intelligent civilizations. Fact 90. SETI's passive listening. The search for extraterrestrial intelligence, SETI, involves using radio telescopes to listen for artificial signals emanating from deep space. These programs scan vast stretches of the electromagnetic spectrum, hoping to detect patterns or messages that couldn't be explained by the natural astrophysical phenomena. The assumption is that an advanced civilization might communicate or leak radio signals as part of their technological development, much as Earth does. It's a patient and painstaking endeavour, like searching for a needle in an astronomical haystack. But the potential reward, confirming we are not alone, is immeasurable. We cast our cosmic ears into the silent void, hoping to hear an echo. The future of exploration, pushing cosmic boundaries. Our journey through the cosmos is far from over. Humanity's innate curiosity propels us ever onward, pushing the boundaries of what we know and what we can achieve. Fact 91. The James Webb Space Telescope's legacy. The James Webb Space Telescope, JWST, represents a monumental leap in our ability to observe the universe. Operating primarily in the infrared spectrum, it can peer through cosmic dust clouds to observe the very first galaxies forming after the Big Bang, study the birth of stars and planetary systems, and analyse the atmospheres of exoplanets for potential biosignatures. Its unprecedented resolution and sensitivity are already revealing the universe in stunning new detail, offering glimpses into cosmic history and the potential for life that were previously unimaginable. JWST is not just a telescope, it is a time machine and a life detector, all rolled into one. Fact 92. Manned missions to Mars and beyond. The dream of sending humans to Mars is sadly moving closer to reality. Organizations like NASA and private companies are developing the technologies and strategies required for extended human missions to the Red Planet. These missions would not only allow for in-depth scientific research, including the direct search for past or present life, but also represent a significant step towards humanity becoming a multiplanetary species. Beyond Mars, concepts for manned missions to lunar outposts, asteroids, and even the moons of Jupiter and Saturn are being explored, pushing the frontiers of human endurance and ingenuity. Our footsteps on other worlds await. Fact 93. Gravitational wave astronomy. A new window to the universe has opened with the advent of gravitational wave astronomy. Detectors like LIGO and Virgo can sense the ripples in space-time caused by cataclysmic cosmic events such as the merger of black holes or neutron stars. These gravitational waves offer a completely different way to see the universe, allowing us to observe phenomena that are invisible to traditional electromagnetic telescopes. This emerging field promises to reveal entirely new aspects of cosmic dynamics, offering insights into the most extreme environments in the universe and potentially even the very first moments of the Big Bang, before light could travel freely. The fabric of reality, space, time, and beyond. Our journey would be incomplete without a moment to contemplate the very stage upon which all these cosmic wonders unfold. Space and time themselves. Fact 94. Space-time as a flexible fabric. Albert Einstein's theory of general relativity revolutionized our understanding of gravity, proposing that it is not a force in the traditional sense, but rather a curvature of space-time caused by mass and energy. Imagine space-time as a colossal flexible fabric. Massive objects like stars and planets create dips or indentations in this fabric, and other objects moving nearby simply follow the curves of this distorted geometry. This elegant concept explains why planets orbit stars and why light bends around massive objects. It highlights that space and time are not separate, static entities, but are intrinsically linked and dynamic, constantly being shaped by the universe's contents. Fact 95. Time dilation. Time is relative. Another profound consequence of general relativity is time dilation, the phenomenon where time can pass at different rates for different observers. This occurs due to two main factors: relative velocity and gravity. The faster an object moves, or the stronger the gravitational field it experiences, the slower time passes for that object relative to an observer in a weaker gravitational field or at a slower speed. This isn't just theoretical, it's a measurable effect, crucial for the accuracy of GPS satellites, which must account for both gravitational and velocity time dilation. Time, it turns out, is not an absolute universal constant, but a personal experience shaped by our motion and location in the cosmos. Fact 96. Wormholes, bridges through space-time, theoretical. The equations of general relativity also allow for the theoretical possibility of wormholes, hypothetical tunnels or shortcuts through space-time that could connect two distant points in the universe, or even different points in time. While often depicted in science fiction as instantaneous travel portals, real wormholes, if they exist, would likely be incredibly unstable and require exotic matter with negative energy density to remain open. Currently, wormholes remain purely theoretical constructs, fascinating mathematical possibilities that push the boundaries of our imagination, inviting us to dream of traversing the vast distances of the cosmos in unimaginable ways. Fact 97. The multiverse theory, beyond our universe, speculative. One of the most mind-bending concepts in modern cosmology is the multiverse theory, which posits that our universe might be just one of an infinite number of universes collectively forming a multiverse. There are several theoretical frameworks that suggest this, including inflationary cosmology, where eternal inflation could spawn countless bubble universes, and string theory, which allows for extra dimensions and parallel universes. While highly speculative and currently untestable, the multiverse concept challenges our anthropocentric view, suggesting that our cosmic home, vast as it is, might be but a tiny speck in an infinitely grander reality. Our place in the cosmic tapestry. As our journey through these 100 space facts draws to a close, we are left with a profound sense of awe and wonder. We have traversed unimaginable distances, witnessed cosmic cataclysms, and pondered the very origins and destiny of existence. Fact 98. Earth's pale blue dot. From the perspective of Voyager 1, 4 billion miles away, Earth appeared as a pale blue dot, a tiny, fragile speck of light suspended in a sunbeam. This iconic image, captured in 1920, is a powerful reminder of our planet's singular beauty and isolation in the vastness of space. It underscores the preciousness of life here and the imperative to protect our home, the only one we know. From this distant vantage point, all of human history, all our joys and sorrows, our triumphs and failures, are contained within that single, luminous point. Fact 99. We are stardust. The atoms that make up our bodies, the carbon in our bones, the oxygen we breathe, the iron in our blood, were forged in the hearts of the ancient stars, scattered across the cosmos in supernova explosions, and eventually coalesced to form our solar system and everything within it. We are literally made of stardust, intimately connected to the grand cosmic cycle of birth, death, and rebirth. This profound realization connects each of us directly to the universe itself, making us not merely observers, but active participants in its ongoing story. Fact 100. The universe within. Perhaps the most astonishing space fact of all is that the entire universe, in all its complexity and wonder, resides not just out there but also within us. Our capacity for curiosity, for wonder, for seeking knowledge and understanding is a testament to the universe's ability to comprehend itself. Through our minds, through our science, and through our art, the cosmos reflects upon its own grandeur. We are the universe's way of experiencing itself, of marveling at its own intricate beauty. As we conclude this chapter, and indeed our journey through these 100 space facts, we hope you feel a deeper connection to the vast, mysterious, and beautiful cosmos. Let the wonders we've explored fill your mind with peace and inspiration. Allow the gentle rhythm of the universe to lull you into a state of deep relaxation. The stars are always there, waiting for you to dream among them. Rest now and let the cosmic ocean carry you into a peaceful slumber. As we gently drift through the cosmic ocean, having pondered the very fabric of space-time and the elusive whispers of the multiverse, we find ourselves ever more connected to the vastness around us. Our journey has revealed that the universe is not just an external spectacle, but an intricate dance in which we too are participants, made of stardust, contemplating stardust. From the pale blue dot we call home, our gaze extends, seeking not just what is visible, but also the hidden forces and invisible messengers that shape the cosmos. Tonight, we delve deeper into these profound mysteries, exploring phenomena that challenge our perceptions and expand our understanding of what is possible. We will listen for the echoes of cosmic collisions, peer into the hearts of incredibly dense stars and track particles that travel unimpeded through galaxies. Allow your mind to gently open to these wonders, letting the sheer scale and ingenuity of the universe wash over you, bringing a profound sense of peace and perspective. Gravitational waves, ripples in space-time. In our last exploration, we touched upon space-time as a flexible dynamic fabric, a concept born from Einstein's theory of general relativity. Now let us truly feel its subtle vibrations. Imagine this fabric not merely as a static backdrop, but as a responsive medium, capable of rippling. These ripples are gravitational waves, disturbances in space-time itself, propagating outward from colossal cosmic events like waves spreading across a pond. These waves are generated when massive objects accelerate violently. Think of the spectacular merger of two black holes, spiraling inward fast and faster until they collide in a cataclysmic embrace, or the fiery dance of two neutron stars before they too coalesce. Such events are among the most energetic in the universe, releasing incredible amounts of energy in the form of these space-time ripples. For eons, these waves travelled across the cosmos, carrying information about their dramatic origins, yet remaining undetectable to us until very recently. The detection of gravitational waves marks a monumental shift in our ability to perceive the universe. Instruments like the Laser Interferometer, Gravitational Wave Observatory or LIGO, are incredibly sensitive observatories designed to measure minute distortions in space-time. They use long L-shaped arms with lasers that measure the precise distance between mirrors. When a gravitational wave passes through Earth, it subtly stretches and compresses space-time, causing these distances to change by an infinitesimal amount, far smaller than an atom's width. Yet these changes are precisely what LIGO and its sister observatories like Virgo are built to detect. Through gravitational wave astronomy, we gain a completely new sense for the universe. No longer are we limited to observing light across the electromagnetic spectrum. We can now listen to the universe's most violent symphony, hearing the chirps of merging black holes and the rumbles of colliding neutron stars. This new window allows us to probe regions of the universe previously hidden from view, such as the interiors of opaque stellar remnants or the moments just after the Big Bang, offering unprecedented insights into the cosmos's most extreme phenomena. It is a profound testament to human ingenuity and the universe's endless capacity to surprise us. The extreme lives of neutron stars, pulsars and magnetars. From the ripples of space-time, let us turn our attention to some of the universe's most extraordinary compact objects, neutron stars. These are the super-dense, city-sized remnants of massive stars that have met their end in spectacular supernova explosions. If a star too large to become a white dwarf, but not massive enough to collapse directly into a black hole, collapses, it forms a neutron star. Imagine squeezing the mass of our sun into a sphere no larger than a city like Manhattan. That's the astonishing density of a neutron star. A teaspoon of neutron star material would weigh billions of tons here on Earth. Among these incredible objects, we find two particularly fascinating types: pulsars and magnetars. Pulsars are rapidly spinning neutron stars that emit beams of electromagnetic radiation from their magnetic poles. As the neutron star rotates, these beams sweep across space, much like the beam from a lighthouse. If Earth happens to be in the path of one of these beams, we observe regular pulses of radiation, hence the name pulsar. These cosmic lighthouses spin with astonishing precision, some completing hundreds of rotations per second, making them more accurate timekeepers than even the most precise atomic clocks on Earth. Their rhythmic pulses have been used to test Einstein's theory of relativity, and even as cosmic navigation beacons. They are a constant rhythmic reminder of the universe's powerful and precise mechanics. Even more extreme are magnetas. These are a rare type of neutron star characterized by incredibly powerful magnetic fields, the strongest known in the universe. A magnetar's magnetic field can be a quadrillion times stronger than Earth's magnetic field. To put that into perspective, if a magnetar were located halfway to the moon, it would strip the data from every credit card on Earth. These immense magnetic fields can cause starquakes on the neutron star's surface, triggering enormous flares of X-rays and gamma rays that are so powerful they can affect Earth's ionosphere from thousands of light years away. Magnetars are truly the most magnetic objects in the cosmos, showcasing the raw, untamed power of the universe. Invisible messengers, cosmic rays and neutrinos. Beyond the visible light and the gravitational whispers, the universe is also constantly sending us messages through streams of invisible particles. These messengers carry information from the most energetic and mysterious corners of the cosmos, silently passing through us, offering clues to phenomena we cannot otherwise detect. One such messenger is the cosmic ray. These are not rays in the traditional sense, but incredibly high-energy particles, mostly atomic nuclei like protons and electrons, that travel through space at nearly the speed of light. They originate from violent events far beyond our solar system, such as supernova explosions, the powerful jets from active galactic nuclei, and perhaps even the vicinity of black holes. When cosmic rays strike Earth's atmosphere, they collide with atmospheric particles, creating showers of secondary particles that can reach the ground. By studying these cosmic rays, we gain insights into the most energetic processes in the universe, understanding the extreme conditions found in stellar nurseries and galactic cores. They are a constant invisible rain from the depths of space, reminding us of the dynamic and sometimes violent nature of the cosmos. Then there are neutrinos, often called ghost particles, because they interact so rarely with ordinary matter. Neutrinos are fundamental particles with almost no mass and no electric charge. They are produced in vast quantities during nuclear reactions, such as the fusion processes deep within the Sun's core, or the catastrophic collapse of a star in a supernova. Billions of neutrinos from the Sun pass through your body every second, completely unnoticed. They're incredibly difficult to detect because they can travel through light years of lead without interacting with a single atom. However, specialized detectors, often deep underground or in ice, are designed to catch the occasional interaction of a neutrino. By studying these elusive particles, scientists can peer directly into the hearts of stars and supernovae, gaining information that light alone cannot provide. For instance, neutrinos were detected from supernova 1987A hours before its light reached Earth, providing invaluable data about the star's final moments. Neutrinos offer us a unique, unobscured view of the universe's most hidden processes, a silent symphony playing constantly through the fabric of reality. Visiting the cosmic web and large-scale structure. As we consider these invisible forces and messengers, let us once again zoom out to the grandest scales of the universe. We have previously touched upon how galaxies group together, forming clusters and superclusters, but the universe's structure extends far beyond these individual groupings, forming what cosmologists call the cosmic web. Imagine the universe as a vast three-dimensional tapestry woven from luminous threads of galaxies and immense empty voids. The cosmic web is precisely this, an intricate network of filaments, walls and nodes, galaxy clusters, that stretch across billions of light years, interspersed with immense, nearly empty regions known as voids. Galaxies are not randomly scattered throughout space. Instead, they are gravitationally drawn together along these cosmic highways and into these dense knots. This large-scale structure is not merely a collection of galaxies, but a direct consequence of the universe's evolution since the Big Bang, profoundly shaped by the invisible hand of dark matter. Dark matter, which we discussed earlier, does not interact with light, but its gravitational influence is immense. It forms the scaffolding upon which ordinary matter, the stuff of stars and galaxies, has collapsed and organized. The densest concentrations of dark matter act as gravitational wells, attracting gas and dust, which then ignite into stars and form galaxies, eventually coalescing into the filaments and clusters we observe. The cosmic web is a testament to the universe's self-organizing power, a majestic architecture on the grandest scales. It's like observing the brain of the universe, with its intricate connections and vast empty spaces, all contributing to a complex evolving system. This colossal structure reminds us that everything, from the smallest particle to the largest galaxy, is interconnected within this grand cosmic design. The multiverse, a realm beyond our own. Our journey has led us to contemplate the very edge of our understanding, from the smallest particles to the largest structures. Now, let us return to a concept that pushes the boundaries of even theoretical physics, the champ or multiverse. We briefly introduced this idea, but let us allow ourselves to gently explore its implications a little further. The multiverse is not a single theory, but a collection of theoretical frameworks suggesting that our universe, the one we inhabit, might be just one among an infinite or finite number of other universes. These concepts arise from various branches of physics and cosmology, each offering a different flavor of what a multiverse might entail. One idea stems from eternal inflation, a model where inflation, the rapid expansion of space after the Big Bang, never truly ends everywhere. Instead, it continues indefinitely in some regions, while in others it slows down, forming bubble universes, like ours. Each bubble could have different physical laws, different constants, and thus entirely different realities. Another perspective comes from quantum mechanics, particularly the many worlds interpretation. This suggests that every time a quantum measurement is made, or a choice is presented, the universe splits into multiple parallel universes, each representing a different outcome. In this view, countless versions of ourselves exist, making different choices and experiencing different realities. Then there is the concept of a truly infinite universe. If space is truly infinite and matter is distributed throughout it, then eventually patterns of matter must repeat. Given enough space, every possible arrangement of particles, including exact copies of our Earth and even ourselves, would eventually occur. It is crucial to remember that the multiverse remains largely speculative, profound theoretical concept that currently lacks direct observational evidence. However, it is a concept that arises from our deepest scientific inquiries, challenging our anthropocentric views and inviting us to consider a reality far grander and more diverse than we can currently comprehend. It is a thought experiment that expands our sense of wonder to an unimaginable degree, hinting at possibilities that lie just beyond the veil of our current perception. Cosmic time and our place, the cosmic calendar. As we reflect on these immense scales of space and the profound nature of reality, let us ground ourselves by considering the vastness of time. To truly grasp the universe's immense history and our fleeting presence within it, we can use a concept popularized by Carl Sagan, the cosmic calendar. Imagine compressing the entire 13.8 billion year history of the universe into a single Earth year, where the Big Bang occurs on January the 1st at midnight, and the present moment is the stroke of midnight on December 31st. January 1st midnight. The Big Bang ignites. The universe begins its expansion. May. Our Milky Way galaxy forms, a sprawling spiral of stars. August 31st. Our Sun and its planetary system, including Earth, are born from a swirling cloud of gas and dust. September. The earliest forms of life emerge on Earth, simple single-celled organisms. December 1st. Complex multicellular life begins to flourish. December 25th. The dinosaurs appear, dominating the planet for a cosmic week. December 30th. The asteroid impact that wipes out the dinosaurs occurs, clearing the way for mammals. December 31st. This is where things become truly astonishing. 11:59 p.m. The first human ancestors appear. 11:59:46 p.m. Recorded human history begins. 11:59:59 p.m. The invention of the printing press, the scientific revolution, and all of recorded modern history happen in the last second of the year. This cosmic calendar powerfully illustrates our place in time. All of human civilization, all our wars, our triumphs, our art, our science, our entire story occupies but a tiny fraction of the last second of a cosmic year. It is a humbling perspective, yet also an inspiring one. In this infinitesimally small moment, we have developed the capacity to look back across billions of years, to understand the forces that shaped stars and galaxies, and to contemplate the very origins and destiny of the cosmos. We are the universe, in a brief moment, reflecting upon itself. Our journey through these 100 space facts is designed to gently guide you through the wonders of the cosmos, from the familiar glow of our sun to the furthest reaches of theoretical physics. As we continue to unravel the universe's secrets, we find not only scientific facts but also a profound sense of awe and interconnectedness. Allow these thoughts to settle gently within you, fostering a deep sense of peace and wonder. The universe is a vast, beautiful, and eternal mystery, and we are privileged to be a part of its ongoing story. Rest now, knowing that the cosmos continues its magnificent dance, always inviting us to look up and wonder. As we gently drift through the cosmic expanse, our journey has unveiled a tapestry woven from the known and the profoundly mysterious. We have touched upon the edges of understanding, glimpsing the grand questions that still stir the scientific soul, the elusive nature of dark matter and dark energy, the speculative whispers of wormholes and the multiverse, the silent challenge of the Fermi paradox, and the enigmatic birth of supermassive black holes. These unresolved mysteries are not endpoints but rather luminous beacons, guiding our gaze ever deeper into the profound depths of space and time. Tonight, we invite you to venture further, to explore the very fabric of reality at its most extreme and its most ancient. We will contemplate the universe's grand architecture, peer into its infancy, and marvel at the physics that governs its most bizarre inhabitants. Let your mind expand, relax, and prepare to absorb the next layers of cosmic wonder as we continue our meditative exploration of the universe's most captivating truths. The architect of immensity, unveiling the cosmic web's grandeur. Our universe is not a uniform, evenly distributed expanse, but rather a magnificent, intricate structure, often likened to a vast three-dimensional web. Imagine shimmering filaments of light, stretching across unimaginable distances, interspersed with immense echoing voids. This is the cosmic web, the largest known structure in the universe, sculpted over billions of years by the relentless pull of gravity, primarily influenced by the invisible hand of dark matter. Within this grand architecture, galaxies are not scattered randomly, they congregate. They coalesce into galaxy clusters, massive collections of hundreds or even thousands of galaxies bound together by gravity. These clusters, in turn, are not isolated islands, but are often interconnected by long, thin strands of galaxies and gas, forming the very filaments of the cosmic web. Where these filaments intersect, we find the densest concentrations of matter, the superclusters. Our own Milky Way galaxy, for instance, is part of the local group, which itself is a minor member of the immense Laniakea supercluster, meaning immeasurable heaven in Hawaiian. This colossal structure spans over 500 million light-years and contains approximately 100,000 galaxies, all slowly drifting towards a common gravitational center. The empty regions between these filaments and clusters are known as cosmic voids. These vast, spherical or elliptical areas are largely devoid of galaxies, containing very little matter, acting as the universe's great empty spaces. They represent the regions from which matter was gravitationally pulled away over billions of years, drawn into the denser filaments and clusters. Mapping this cosmic web, understanding its formation, evolution, and the distribution of matter within it, is a cornerstone of modern cosmology, offering profound insights into the universe's history and its future. It is a testament to the power of gravity and the fundamental non-uniformity of our cosmos, a grand design that continues to unfold before our eyes. Echoes of creation, the universe's earliest moments. We have previously journeyed back to the Big Bang, the moment our universe began its expansion approximately 13.8 billion years ago, and observed its afterglow in the cosmic microwave background, CMB. But what transpired in the fleeting moments before the CMB formed in the universe's absolute infancy? This era, shrouded in extreme energy and temperature, holds some of cosmology's most profound secrets. One of the most compelling theories explaining the universe's earliest moments is cosmic inflation. Proposed to address several puzzles left unanswered by the standard Big Bang model, inflation posits that the universe underwent an incredibly rapid exponential expansion in a tiny fraction of a second, from about 10 to 36 to 10 to 32 seconds after the Big Bang. During this unimaginably brief period, the universe expanded by a factor of at least 10^6, smoothing out any initial irregularities and stretching tiny quantum fluctuations into the seeds of the large-scale structures we observe today, like the cosmic web. Before and during this inflationary period, the universe existed as an extraordinarily hot, dense, primordial soup of fundamental particles and energy. In these first instants, quarks and gluons, the building blocks of protons and neutrons, existed freely alongside leptons like electrons and neutrinos, bathing in a sea of high-energy photons. As the universe expanded and cooled, these fundamental particles began to combine. Quarks coalesced to form protons and neutrons, and later, during cosmic nucleosynthesis, these protons and neutrons fused to create the lightest elements: hydrogen, helium, and trace amounts of lithium. The theory of cosmic inflation offers elegant solutions to the horizon problem: why distant parts of the universe appear to have the same temperature despite not having had time to interact, and the flatness problem: why the universe's geometry appears perfectly flat. It suggests that the entire observable universe originated from a tiny region that was in causal contact, and that the immense expansion flattened out any curvature. While direct observational evidence for inflation remains elusive, its predictions align remarkably well with the subtle patterns observed in the cosmic microwave background, making it a cornerstone of our understanding of the universe's birth and early evolution. It is a testament to the universe's dynamic and extreme beginnings, a period of breathtaking transformation that laid the groundwork for everything we see today. Where physics breaks: the extreme realms of black holes and beyond. Our exploration of black holes has revealed them as regions of space-time where gravity is so intense that nothing, not even light, can escape. But what happens if you venture too close, or even beyond the event horizon, that point of no return? The physics in these extreme environments challenges our very understanding of reality. One of the most dramatic fates awaiting any object that falls into a black hole is spaghettification. Imagine being stretched and squeezed by an invisible, irresistible force. As an object approaches a black hole, the gravitational pull on the part of the object closer to the black hole is significantly stronger than the pull on the part farther away. This differential force, known as a tidal force, stretches the object vertically along the direction of gravity and compresses it horizontally, much like pulling on a piece of spaghetti until it breaks. For a human, this would mean being stretched into a long, thin strand of atoms before reaching the singularity. While larger, supermassive black holes have weaker tidal forces at their event horizons, allowing an object to cross relatively intact before spaghettification occurs deeper inside, smaller stellar mass black holes would spaghettify an object long before it even reached the event horizon. Beyond spaghettification, rotating black holes, known as Kerr black holes, introduce another mind-bending phenomenon: frame dragging. According to Einstein's theory of general relativity, a massive rotating object drags space-time around with it. For a rotating black hole, this effect is so profound that it creates a region called the ergosphere, located outside the event horizon. Within the ergosphere, space-time itself is forced to rotate with the black hole, making it impossible to remain stationary relative to a distant observer, even if you are moving at the speed of light. Objects entering the ergosphere are inevitably swept around, gaining or losing energy in a process that could theoretically be harnessed for energy extraction, known as the Penrose process. And while black holes are defined by their inescapable gravity, theoretical physicist Stephen Hawking proposed Hawking radiation, suggesting that black holes are not entirely black. Due to quantum effects near the event horizon, pairs of virtual particles, a particle and an antiparticle, are constantly popping into existence and annihilating each other. If one particle falls into the black hole and its partner escapes, the escaping particle carries away a tiny amount of the black hole's energy, causing the black hole to slowly lose mass and eventually, over an immense timescale, evaporate. This concept elegantly bridges quantum mechanics with general relativity, though it remains a theoretical prediction yet to be directly observed. Beyond black holes, neutron stars also represent realms of extreme physics. These stellar remnants, born from the supernovae of massive stars, are incredibly dense. A sugar cube of neutron star material would weigh billions of tons. Their interiors are thought to harbour exotic states of matter, far beyond anything we can replicate on Earth. Scientists hypothesize the existence of quark-gluon plasma, a state where quarks and gluons are no longer confined within protons and neutrons, but move freely, or even stranger strange matter, composed of up, down and strange quarks. Studying these objects through their gravitational waves or electromagnetic emissions provides invaluable insights into the fundamental forces and particles that govern our universe under the most extreme conditions imaginable. The invisible universe, probing dark matter and dark energy further. Our journey has repeatedly brought us face to face with the universe's most profound enigmas. Dark matter and dark energy. Together, they constitute about 95% of the cosmos, yet their true nature remains stubbornly hidden. Despite decades of intense research, these invisible components continue to challenge our understanding, pushing the boundaries of physics and astronomy. The evidence for dark matter is overwhelming, inferred from its gravitational effects on galaxies and galaxy clusters. Galaxies rotate too fast to be held together by their visible matter alone, and galaxy clusters exhibit gravitational lensing effects that require far more mass than we can see. Scientists are actively pursuing several avenues to directly detect dark matter particles. Experiments like those at the Large Hadron Collider LHC seek to produce hypothetical, weakly interacting massive particles, WIMPs. One of the leading candidates for dark matter by smashing particles together at extreme energies. Other experiments, buried deep underground to shield them from cosmic rays, are designed to detect the faint interactions of WIMPs passing through the Earth. These include detectors filled with ultra-pure liquids like xenon or germanium, waiting for a rare collision between a WIMP and an atomic nucleus to produce a detectable flash of light or ionization. Still other theories explore alternative candidates like MACOs, massive compact halo objects. Dark condensed objects like black holes or brown dwarfs, though these are now largely disfavored. The search is a testament to humanity's relentless pursuit of the unseen, a quest to complete our cosmic inventory. Dark energy, the mysterious force driving the accelerating expansion of the universe, presents an even greater puzzle. Its existence was discovered through observations of distant supernovae, which appeared fainter than expected, implying they were farther away due to an accelerated expansion. The simplest explanation for dark energy is the cosmological constant, a concept proposed by Einstein himself, representing the energy inherent in empty space. However, theoretical calculations for this energy yield a value vastly larger than what is observed, leading to one of the biggest discrepancies in physics. Alternative theories, such as quintessence, propose a dynamic, evolving energy field that changes over time, rather than a constant. Scientists are using large-scale surveys of galaxies and the cosmic microwave background to precisely measure the expansion history of the universe, hoping to distinguish between these competing models and ultimately uncover the true nature of dark energy. This frontier of cosmic discovery is where our current understanding truly breaks down, inviting new paradigms and perhaps even a revolution in physics. Windows to the unknown. future observatories and breakthroughs. Our current generation of observatories, like the magnificent James Webb Space Telescope JWST, is already pushing the boundaries of what we can see and understand. Yet the thirst for knowledge drives us to conceive of even more ambitious instruments, designed to pierce deeper into the universe's past, uncover more exoplanets, and directly probe the most elusive cosmic phenomena. For studying exoplanets and searching for signs of life, future space telescopes like the proposed Large Ultraviolet Optical Infrared Surveyor LUVOIR and the Habitable Exoplanet Observatory HABEX aim to directly image Earth-sized exoplanets and analyze their atmospheres for biosignatures. These colossal instruments, with mirrors many times larger than JWST's, would utilize sophisticated coronagraphs to block out the blinding light of parent stars, allowing us to see the faint glow of orbiting worlds and potentially detect the chemical fingerprints of life. The nascent field of gravitational wave astronomy is set for a major leap with projects like the Laser Interferometer Space Antenna, LISA. Unlike ground-based detectors such as LIGO and Virgo, which are sensitive to high-frequency gravitational waves from stellar mass black hole mergers, LISA will be a space-based constellation of 3 spacecraft, orbiting the Sun in a triangular formation, separated by millions of miles. This immense baseline will allow LISA to detect low-frequency gravitational waves generated by supermassive black hole mergers, the inspiral of white dwarfs, and even echoes from the very early universe, opening an entirely new window onto cosmic history. To further unravel the mysteries of dark matter, dark energy, and the most energetic events in the cosmos, neutrino telescopes are growing in sophistication. Observatories like IceCube at the South Pole and the future KM3 Net in the Mediterranean Sea are designed to detect high-energy neutrinos, elusive particles that travel across the universe unimpeded by matter or magnetic fields. These ghost particles offer direct probes of extreme cosmic accelerators, such as supernovas, active galactic nuclei, and gamma-ray bursts, allowing us to study processes hidden from an electromagnetic radiation. And for mapping the universe on its grandest scales, projects like the Square Kilometre Array, SKA. An international radio telescope project under construction in Australia and South Africa will revolutionise radio astronomy. With thousands of dishes and millions of antennas, the SKA will be able to detect faint radio signals from the early universe, trace the distribution of hydrogen gas across cosmic distances, and search for technosignatures from distant civilizations with unprecedented sensitivity. These next-generation observatories represent humanity's collective ambition to understand our universe, pushing the boundaries of technology and scientific ingenuity to reveal the secrets that still lie hidden in the cosmic ocean. Our continuing cosmic journey, a call to wonder. As our journey through these cosmic facts draws to a close for tonight, we reflect on the immense scale of what we have explored, from the intricate dance of galaxies in the cosmic web to the fleeting, fiery moments of the universe's birth and the mind-bending physics at the edge of black holes. We have acknowledged the vast unknowns, the dark matter and dark energy that continue to challenge our deepest scientific theories, and the future observatories poised to unveil new wonders. The universe is a boundless realm of discovery, a place where every answer often leads to a dozen new questions. It is a testament to the enduring curiosity of the human spirit that we continue to gaze upwards, to listen and to probe, seeking to understand our place within this grand, evolving narrative. As you prepare for rest, carry with you this sense of awe and wonder. Remember that the same fundamental particles forged in the heart of stars and scattered across the cosmos reside within you. You are an integral part of this magnificent story, a conscious observer in a universe that is constantly revealing its secrets. May the quiet contemplation of these cosmic truths bring you a profound sense of peace and connection, reminding you that even in the greatest mysteries, there is beauty, and in every unanswered question, an invitation to dream.